In thinking about algorithms for various game theoretic solution concepts, we've seen several cases where an equilibrium can be efficiently computed using linear programming. For example, in a two-player zero-sum game, we can take advantage of the minimax theorem and build a linear program to find the min-max strategy, which is part of a Nash equilibrium profile. And likewise, in a two-player game, we can use linear programming to identify a strong Stackelberg equilibrium. And we've seen that both correlated and coarse-correlated equilibria can be computed by linear programming in any finite normal form game. So because we can write down a linear program for any of these problems, and because we have libraries that solve linear programs in polynomial time, that gives us efficient algorithms for computing these sorts of equilibria. But so far, our attempts to find Nash equilibria in more general games have come up empty. In two-player general-sum games, we saw a linear complementarity programming approach, but because we had to consider all possible support sets and write separate linear programs for each, there was an exponential number of linear programs, and therefore our algorithm to find a Nash equilibrium takes exponential time. And when we go beyond two players, the complementarity program becomes nonlinear. So in addition to having an enormous number of support sets to check, we don't have an efficient way to check for a Nash equilibrium under those supports with mathematical optimization. But just because the approach we've been using so far doesn't give us an efficient algorithm for finding Nash equilibria in the general case, doesn't necessarily mean that there's no other approach we could use to efficiently compute Nash equilibria. And so we want to ask, is there some other approach that will give us an efficient algorithm for Nash? Or can we prove that the problem of finding a Nash equilibrium is so hard that no efficient algorithm can exist? And so this leads us to thinking about proving a statement along the lines of no polynomial time algorithm exists for computing Nash equilibria in general games. But unfortunately, we don't know how to prove that sort of claim. In fact, that sort of proof has been stumping computer scientists for decades. The famous P not equal to NP conjecture is about proving that polynomial time algorithms can't exist for certain problems, and that conjecture has been unresolved since the 1970s. In fact, John Nash made a closely related conjecture back in the 1950s for which we still don't have a proof. So instead of trying to prove that the problem can't have a polynomial time algorithm, we start from some problem that is conjectured to be hard, and hopefully one for which there is good evidence of that hardness, and then try to show that the problem we're interested in is at least as hard as the one we already believe to be difficult. And we show that using polynomial time reductions. In this context, a reduction is a way of translating an instance of one problem into an equivalent instance of another problem, so that by solving the translated problem, we can get an answer for the original problem. And this is the sort of thing we do all the time in computer science. If we have a library that lets us solve a particular kind of problem, like, for example, a linear programming library, then by translating a problem we don't yet know how to solve into one that the library knows how to answer, we can get an answer to our original problem. That's exactly how we computed correlated equilibria. We translated the problem of, here is a game, I want a correlated equilibrium, into the sort of thing that the linear programming library knows how to handle. and then we just called that library as a subroutine in our algorithm for finding correlated equilibria. And the part of this process that we call a reduction is the translation from one type of problem to another. And so if we have a problem that is, find me a correlated equilibrium in this game, and we can translate that into a problem of solve the following linear program, then we have done a reduction from the correlated equilibrium problem to the linear programming problem. And as long as that translation takes polynomial time, then that is a polynomial time reduction from the correlated equilibrium problem to the linear programming problem. So when we translate one problem to another, if the translation is efficient, and we know how to efficiently solve the target problem, then this whole procedure gives us an efficient algorithm for solving the original problem. So one way we can think of what this polynomial time reduction tells us is that if we have an efficient algorithm for solving problem A, then the reduction gives us an efficient algorithm for solving problem B. But since this is an if-then statement, whenever we prove the statement, we also prove its contrapositive. Those are logically equivalent. So if our reduction proves the statement that if there is an efficient library for A, then there is an efficient algorithm for B, the reduction also proves the contrapositive of that statement. The negation of this implies the negation of this. So if we come up with a way to translate instances of problem B into instances of problem A, that proves that if there is no efficient algorithm for B, there cannot be an efficient algorithm for A. Another way to think about this is this whole procedure gives a polynomial time algorithm as long as both steps happen in polynomial time. But if we somehow know or believe that there can't be a polynomial time algorithm for B, but we can do the translation step in polynomial time, then there must not be a polynomial time algorithm for A, otherwise that would contradict our belief that we can't efficiently solve B. So we can use this sort of translation to show if we already think this problem is hard, then this problem must be at least as hard. So this gives us a way of showing that a problem is hard to solve. If we have some problem where we think it can't have a polynomial time algorithm, and we can translate that into some new problem, as long as the translation takes polynomial time, that means the new problem also can't be solved in polynomial time. So what we need now is a starting problem that we think is hard. And for our purposes, that starting problem will be two-player general sum Nash. We'll talk more soon about why we think this particular problem is hard, but for now, let's take as an assumption that two-player general sum Nash is difficult to solve, and show that other problems are at least as hard. And that means we need to perform a reduction where we start with the problem that we already think is hard to solve and translate it into another problem that we want to show to be hard. So here we are performing a reduction from two-player general sum Nash to three-player zero-sum Nash. And what that would tell us is that even though two-player zero-sum is efficiently solvable, three-player zero-sum is not, because by this translation we'll show that if we can efficiently solve three-player zero-sum Nash, We'll also be able to solve two-player general sum Nash, which would be a contradiction if we think that two-player general sum Nash is hard. So our reduction needs to translate any two-player general sum game into a three-player zero-sum game such that the answer to the problem is preserved. When we solve the resulting instance of three-player zero-sum, we will get an answer that tells us the Nash equilibrium of the original two-player general sum game. And our reduction does that by taking as input a two-player general sum game. So we have two players where player 1 has n actions and player 2 has m actions. And in each cell of the payoff matrix, we have a utility for player 1 and a utility for player 2. And those utilities can be any numerical value, because this is general sum. And we want our reduction to transform this game into a new game that is three-player zero-sum, but such that the Nash equilibria of the three-player game will tell us the Nash equilibria of the two-player game. And we do that by adding a third player who has only one action. Since they have only one action, we don't need separate matrices for their other actions. And now we just need to add to every cell in the payoff matrix player 3's utility in that cell. And we can set the utility for player 3 in any given cell to minus the sum of the other player's utilities. So for the cell where player 1 chooses action X and player 2 chooses action Y, we'll take their two utilities, add them up, and give player 3 minus that utility, which ensures that the sum of utilities in that cell is 0. And if we do that to every cell in the payoff matrix, now we know the sum of payoffs in any cell is 0, and so we have a three-player zero-sum game. Now if we somehow computed a Nash equilibrium in this three-player zero-sum game, then we know that player 3 is just playing 100% probability on their only action. And so if we drop that strategy for player 3 and just look at the strategies for player 1 and 2, the resulting profile must be a Nash equilibrium of the original game. Because if player 1 is best responding in the three-player game, they face exactly the same incentives in the two-player game, so the same strategy would also be a best response in the same profile there. So we have shown that if there were an efficient algorithm for solving this three-player zero-sum game, that would also give us an efficient algorithm for solving the two-player general sum game. But since we are assuming that two-player general sum Nash is hard, that means there can't be an efficient algorithm here. So there must also not be an efficient algorithm for solving three-player zero-sum. So we've shown that three-player zero-sum Nash is at least as hard as two-player general sum Nash, which is why when we talk about zero-sum games, we're almost always referring to two-player zero-sum games, because they are efficiently solvable, whereas three-player zero-sum games are not, as long as we're right about our conjecture that general sum Nash is hard. And now that we have another problem that we think is also hard to solve, if we were to reduce three-player zero-sum Nash to yet another problem, that would show that the new problem is also at least as hard as two-player general sum Nash, and so we think that new problem can't have a polynomial time algorithm. And this will be our general approach to showing that problems are hard, as long as we have a starting point of a problem we're convinced will be difficult to solve. We can do translations that reduce that problem to others, and then chains of translations that reduce to still more problems, showing that as long as that first problem has no efficient algorithm, none of the problems that we can reduce it to by any chain of translations can be easy to solve.